does to a function of the fields phi is it replaces phi at x by phi at theta of x. And then I said, suppose we have a model with the following property. Suppose the model has the following property, which I called Osterwalder-Schrader positivity, OSPOS. The property is that if f is a function of phi of x, where the only fields that occur, which it really depends on, are in the plus half. So let's call this there's like a right-hand side and a left-hand side under this reflection, and I want to talk about the right-hand side, lambda plus here. Suppose that this particular function actually doesn't depend on the fields on the left-hand side. It just depends on the fields on the right-hand side. And it can be any function. Then the expectation of f, theta f of f, we'd like that to be, this is a condition. We'd like it to be greater than or equal to 0. It's a form of positivity for any function f. That's the property called Osterwalder-Schrader positivity, if you have that for any function f. So suppose we have a model where we do have that. Then we can do something remarkable to prove that this ratio ZH over Z0 is less than 1. And it goes like this. From this, you first deduce that if you put two different functions in here, f and g, and take their expectation, that I forgot probably to put the absolute value in this morning, but the absolute value of that expectation is less than theta f square rooted theta g square rooted. So this is Cauchy-Schwarz inequality. I'm not going to tell you how you get that, but basically what you do is to just apply this to the case where f is f plus g and f minus g, and square it out and get something like that. So there's a little step here where I'm missing some details, but you get it from here. And now I'll show you what we want to do by drawing lots of little faces. So there's an inequality coming up. So there's one thing, and then there's the next implication. And what I'm going to do is to draw a picture to show you what I want to do, and then underneath I'll write the equation that the picture means. So let's take a periodic lattice. This is a very small lattice. There's a site, a site, a site, and a site, and if you have to think of them as a ring, they're coupled. I mean, it's like they're coupled together by nearest neighbor interactions like that. This is a very small lattice, but you can do the same thing on any size lattice. And we have, at each site in this lattice, we have a slightly different one of these. That's different at each site. And somehow what we want to do is to make them all the same as a bound. So I'll symbolize the fact that they're different by drawing different patterns here. That just means that put something different in the way of a single spin measure at each one of those sites. Now, what we do is we use this bound above here with this reflection about here. The sites are the faces, that's right, yes. And I'm just trying to show you that there's something different at each site by drawing these little icons here. And what we're going to do is to do a reflection about this thing here. So we're going to take this to be, what's on here is the f, and what's on here is the g in this inequality. So the square roots of these square roots, it's a new expectation. It looks like this. That will become that, and this one will be that, right? And now you can see what I'm going to do to each of these. Now we'll do you see, you have the reflection that I postulated. I should be saying here, the reflection that I postulated is one that you can, by translation invariance, you can do it about any hyperplane. And not only that, but if there's more than one direction, in more than one dimension, I also want to be able to do the reflections in the other hyperplanes as well, which is true for an isotropic kind of model. So now I'll take each one of those and I'll reflect it about there. Well, I won't write it all out, but you can see what's going to happen. There'll be 4 of them, each to the power of 1/4. And now they'll be homogeneous.
Sorry.
Just a second, I'll finish it and then we'll be ready. So I'm now doing reflection. I'm doing a reflection in this one about that hyperplane. Yes?
So you're assuming a certain division of your lattice into 2 parts, or?
Yes, I'm assuming that, so in this case here, for example,
so
I'm assuming that any of these reflections, you have this positivity property.
So this restricts your class of lattices then?
Well, it just means really not so very much, because if I have one of these reflections, I get all the translates of that reflection, which in this case here, for example, if I have it here, because the model's translation invariant, which is rotating the ring, I will have it about there as well. So I think really the only real restriction here is to say that I have all of the reflections at any given point in the lattice, and then I can move them around by translation and have them at any other point. That's one reason why I wanted to use periodic boundary conditions, to have that property. Just to finish this off, you see that what this has done is I've reflected those 2 down to here to make them all the same. And then I'd have one that looks like this, and so on. All the 4 properties would be there. And now, if you look at what this is, this means that I have made the translation. So each one of these symbolized the fact that in this model here, I had an hx that depended on x. What I have done now is to make them all constant. Now you remember, so this is a model where there's an hx which is the same at this site, and this site. They're all the same. And you remember that when I remarked earlier that if you have h as constant, it's the same. You can just translate it out. So you can remember that remark. If the h of x's are all constant here, well then you can make a uniform, a constant translation of the phi, and it will disappear. So you get rid of it. So this is equal to the same thing multiplied by itself, z of 0 to the power of 1/4 4 times. So in other words, it's z. And I don't think, maybe I won't write down the equation. I think I've explained the idea well enough here, perhaps, unless anybody wants to ask more. The reflections enable you basically to make the h of x constant. And, and then you have this bound. So that means back up here, this is less than 1. So you have Gaussian bound, and that leads to the proof of symmetry breaking. Now, what kinds of models? Yes?
Perhaps we could say again the word why intuitively, several physicists that should also hold more generic cases, so if one has no such symmetry. So I have no intuition if I start wobbling around this balls, why my partition function should get smaller.
Why it should get smaller? Oh, because, so intuitively, The reason is because the effect of translating wobbles the spheres. So if you translate these spheres a little bit, up or down, this grad phi doesn't really like it very much because some of them, some of them are moved up relative to the others. It seems almost for sure that it will add extra energy into it to wobble them about their centers. I don't know whether you find that convincing or not, but you basically, you should draw them on top of each other, right? There's a site, and then a next door site, and the spin is like that. Then there's a next door site, which I'm going to draw on top, but it's actually on a wobbled thing like that, and the spin is there. And for sure, where they're all the same is going to be either a maximum or a minimum, and you just have to ask yourself which it's going to be, right? But that's a very intuitive argument, and you need something like this, so you need something extra. So that's a kind of frontier to come up with a way to get bounds on these sorts of objects, which are not too strenuous and don't make us die of exhaustion trying to get them, because there are other methods to get this sort of thing, but they're really hard work. Now, what kinds of models have this? Well, there are two things I want to say now. What kinds of models actually have this property of having such a theta? So just quickly, let's look at the Ising model. I need to say this because it's something that hasn't come up about statistical mechanics yet, and it's such an important property. So the Ising model in one dimension, again, just for illustration purposes, I'll take an Ising model which is on a lattice bent into a ring like this in one dimension. So the partition function is the sum of e to the beta sigma I plus 1, where I runs from 1 to n. I can write I'm labeling the sites 1, 2, 3, 4, 5, 6, and then so capital N is 6 in this case, but then when you go one further, you couple them together, so I'm using I plus 1, n plus 1 is equal to 1. It's a mod n thing, so that bends them into a ring like this, right? Now, here's a very clever thing that Lentz Ising noticed long ago. This is Ising's thesis. This is, in fact, the product of n matrices multiplied together, which is called the transfer matrix. And what you do to see this is you define T. Now, the rows and columns of this matrix are labeled by sigma, sigma prime. This sigma, oh, I'm sorry, this is rubbish here. I'm trying to sum over spins. I'm very disappointed that nobody objected. It's a sum over spins which assign a -1 or a 1 to each point in lambda. And so the spin configuration is like sigma 1, sigma 2 like that, to sigma n.
I think you need a sum in the exponential.
And that's the sum I want. Right, there is a sum here. Thank you. That's the one from 1 to n. I thought there should be a sum somewhere, right? That looks a little better. Now, T sigma sigma prime, what we're doing is we're just taking one spin, sigma, which is +1 or -1, and sigma prime is the same thing. And it's this matrix, e to the beta sigma sigma prime. If I write it out as a 2 by 2 matrix, taking sigma and sigma prime both to be 1, I get e to the beta. Here I get e to the minus beta, e to the minus beta, e to the beta. It's a very simple 2 by 2 matrix. And what I want to rush past, because it's a wonderful thing for you to think about on your own, is that this sum over all the sigmas being plus or minus 1 is actually multiplying this 2 by 2 matrix by itself over and over again, so that actually Z is equal to the trace of e to the of t to the n. That's called the transfer matrix, this T. Now, once you have a transfer matrix, and if the transfer matrix has positive eigenvalues, so T has positive eigenvalues, or at least non-negative eigenvalues, non-negative eigenvalues, then you will have Osterwalder-Schroeder positivity because, and I'll just draw a picture to illustrate it. Take your model, and there are some spins on the right, on the left, and there are some spins on the right. And don't worry too much about all the t's. There's a t multiplying things together. Just glom that all together into one object, and glom that all together into one object, and there's one single t in the middle. So you can write any of these expectations, f of g. F lives over here, and g lives over there, but none of it should cross the divide here, which is where I want to do my theta. You can write it as an inner product of f with a t in the middle and a g, like that. Now, if you do that, this is an inner product because this is a positive matrix. So you have the property you want. So F lives on here and G lives on there to do this. And that's that. So the theta comes from the transfer matrix. Yes.
What is this cyclicity then?
Ah, that's yeah. Yes. Thank you very much. I screwed something up here. It's really T tensor T. There are two T's. Thank you. Sorry about this.
In higher dimension, there will be a surface. It's
Yeah.
a dividing surface of these.
So this picture here wasn't quite right. I've got it right in my notes, I think. I should have drawn a torus. And there's something on the left half, and there's something on the right half. And when I write T tensor T, I mean that there's a T up here and there's a T down there. And that's the way to do it. So that's why this model, Ising model, and in fact why all these models have this theta positivity. The interesting thing is, which is what Osterwalder and Schroeder were interested in, is that the process is reversible. If you're given a model with this theta positivity and translation invariance, then you can rewrite it in terms of a transfer matrix. And I think I will stop there because that finishes the proof. What I will have done in my notes is to list some really annoying cases where we don't have Osterwalder-Schroeder positivity, just to show you how absurd this way of proving this kind of result is, so that you'll be inspired to come up with another way of getting bounds on this ratio.
What example would there be, let's say, in 1D that doesn't satisfy?
Just take next to nearest neighbors.
Oh, next to nearest.
Just put next to, so make it more ferromagnetic, and you obviously this property is going to still hold, but we can't prove it by this method.
So it will be 4x4 transfer matrix.
Then it'll be a 4x4 transfer matrix, right? Yeah.
Any disordered system, any disordered model will not have this property.
Well, yes, because of the randomness. But if you, yes, that's true. Well, it might have the property. It might still have the property, but you'll have to reflect. When you do the reflection, you'll have to reflect the disorder as well, which you might not want to do. So that's my end there. Thank you very much.